Oh, I'm sorry. Yeah, there's more cons than pros. Okay, that's a fair criticism. Well, besides criticizing, let's make sure that we understand this completely. So what is the probability after this has happened that everybody knows other people are sending? What is the probability of a successful transmission in a given slot? Successful transmission means only one person sends, because if nobody sends, that's a failure. If 2 sends, it's a failure. 3 sends, it's a failure. Okay? So what is the probability of success in this model? So let me start by saying, let me just think from the point of view of 1. The probability that 1 will send a packet in the next slot is going to be 1 by 3, right? And what is the probability that nobody else will send a packet in the slot that 1 sends a packet? What is the probability that 2 will not send a packet in that slot? Sorry? I can't hear you. What is the probability that 2 will send a packet in the second slot? 1 by 3, right? Everybody's is 1 by 3. So what's the probability it will not send a packet? 2 by 3, right? So the probability that 1 will send a packet is 1 by 3. Probability that 2 will not send a packet, that's the second condition for success, is 2 by 3. And the probability that 3 will not send a packet, they're all clones, so 2 by 3. So this equals 4 by 9, right? No, 4 by 27. So the probability that 1 will send something successfully is 4 by 27. What is the probability that 1 or 2 or 3 will succeed in a given slot? Multiplied by? Sorry? 1/3? Is that 1/3? Should I multiply by 1/3? It's actually the other way around. You multiply by 3. This was the probability that 1 will succeed, and there's an equal probability that 2 will succeed, and an equal probability that 3 will succeed. We've already taken care of the collations in this thing. So this is so the total probability that any given slot will be productive is 4 by 9, so which is, I don't know, 45% or something like that. Okay. So if you try to work this, so everybody follow the basic calculation. Okay. So if you try to work that here for n nodes, and as n becomes really large, then so basically if there are n nodes, then the term is, and each one is sending with a probability p, then the term is something like this. So on any given slot, one node can send with probability p. The probability that none of the other nodes sends, each one has a probability of 1 minus p of not sending. So 1 minus p multiplied by 1 minus p to n minus 1. You multiply by n, and you get something like this term, and if n goes to infinity, you try to work this out, you get you work this out, and in the best case, you get a 37%. If the probability is set. So this other question, it's not necessarily the case in here that 1 by 3 is the best probability. Just because there are 3 nodes doesn't mean setting the probability to 1 by 3 is the best way to go. Maybe you're better off if you set it to 1 by 4. Maybe you're better off if you send it to 1 by 2. So you have to work for each one of those and figure out what is your success rate with each of those probabilities. Okay. So with n nodes, if you set the probability, the optimal value, then it comes to 37%. So the basic idea is that 2/3 of your slots will always be wasted, okay, or 2/3 or so. So you can, at best case, you get 30–40% success. Any questions on Aloha? So since there is slotted Aloha, there must be an unslotted Aloha, and there is such a thing as unslotted Aloha. The difference is that you still have fixed size frames, okay, but you don't wait for any particular interval. So everybody has their own clock. So you still have the probability and everything, but things are not synchronized. As soon as you get data, you start sending. You got data here, you start sending. You got data here, you start sending. So you don't have this rigid rule that you can always send only at 1 millisecond, 2 milliseconds, and 3 milliseconds. Okay. So the good thing about this is that you don't need global synchronization anymore. The bad thing is that initially, if yellow was sending here, the only way you could have a collision was if somebody picked exactly the same slot when it was slotted. Now it's unslotted. Anybody starting anywhere here or anywhere here is going to collide. Okay. So your probability of a collision actually doubles. Because it's not just for this slot. You can have half here, half here. So I don't know if it's that clear or not. Initially, the slot had to be this one or this one or this one for sending. And you are good with this, you're good with this, and this was bad. Okay. Now it's unslotted. Anybody who starts from anywhere from here to here is going to cause a collision. If you start here, start here, start here, because there's no this discretization. Okay, so you're more likely to have a collision. That makes sense because you're not doing at least partial synchronization. So basically, disadvantage, less efficiency, more collisions. Advantage, you don't need synchronization. So if you try to work that out, that comes to even worse, same situation, and your probability of success is only 18% for n nodes when n is large versus 36% for slotted. Okay. Any questions? Okay. We just have, I'm going to just cover, there's only a little bit more in terms of MAC protocols. The next one is CSMA, Carrier Sense Multiple Access. The idea is listen before you transmit. So this is a new idea or from what we've been discussing so far. It's very simple. You don't just start sending. You listen to the channel, and if somebody else is sending, then you just wait. And the moment you see that the channel is free, nobody else is sending, you start sending. Okay. So that's why it's carrier sense multiple access. So if channel is busy, wait. Channel is idle send, kind of like when, like human conversation. If somebody is going on and on and on, you generally let them talk and finish their sentence or finish their paragraph. You do not just start talking whenever you feel like. Some people may do that, but generally polite people will wait for somebody to finish and then you start talking. So that's the basic. CSMA. So now the question is, can collision still happen? Even though in a polite conversation you wait for somebody to finish talking before you start talking, you will still find that sometimes you start talking and the other person starts talking at the same time, right?